Hey everybody, it is Mrs. Spivey. We are finally in Unit 11, our last unit of Chem 1. So what you need to be successful today, you need your Unit 11 book, you need a periodic table. You may or may not you won't need a periodic table explicitly today, but you can have one out just in case you need it, because it is chemistry class and we love our periodic table. So Unit 11, we're going to talk about gases, okay? So I have a couple of notes that are going to be on the screen for you to see. If you need to pause the video and copy the notes down, sorry. I am at school, so that was one of the lunch bells. So if you ever need to pause the video and copy down what's on the screen, please do, because I'm not going to necessarily pause and give you time to write like I would be doing in class. So gases, just some general properties of gases that are important to us. Gases can be compressed, so that means that they can be put in like a tank. So think about if we have helium in a tank and you need to fill up some balloons, okay? Gases also diffuse. So my usual go-to example of this is if you're walking by, say the locker rooms at the high school, and in the hallway you can smell like the Axe deodorant spray. Okay, so those gas molecules are diffusing, they're moving, they're spreading out throughout the environment. So they spread out. Okay, gases also exert pressure. So some typical units for pressure that you're going to start seeing in our problems: millimeters of mercury, mmHg, atmosphere, kilopascal, and torr. Now this kilopascal, you could also just see a regular Pascal, like no prefix in front. Gases fill the available space, so you don't think about the room that you're being in as that you are currently sitting in as a container, but it is. So the air that we're breathing is filling the available container, it's filling the space. And gas molecules also have mass. Okay, now from these general properties of gases comes a very important theory to us called the kinetic molecular theory. So the kinetic molecular theory is important for us because it helps us, it makes assumptions for gases that we can use when we are doing math and when we are making observations. Okay, so the kinetic molecular theory gives us some generalizations for gases. Okay, some things are kind of like a hand wave. It's our way as chemists to kind of make some approximations that make our math work out. So once you leave Chem 1 and you take like dual enrollment Chem or AP Chem, you're going to learn more about how real gases behave. Okay, so in general, gas particles are in constant random motion, which is something that you've learned about since like the 3rd grade. Gas molecules have no forces of attraction. So that means like if I have nitrogen gas and oxygen gas in a container, kind of like the air that we're breathing. So gas molecules have no forces of attraction. So that means that the nitrogen molecules and the oxygen molecules are in the same container, but they're not attracted to one another like a magnet. Number 3, gases have a negligible volume compared to the distances between them. So that just means that a gas molecule doesn't take up too much space on its own individually. So remember, volume is the amount of space that an object takes up. So one gas molecule is going to have a very negligible volume. And number 4, collisions between the particles are elastic. So elastic means that no energy is lost. So if I'm looking at this container of nitrogen and oxygen again, the molecules, they are bumping into one another, and energy is being transferred from one molecule to another, right? What this elastic is meaning is all of the energy from a nitrogen molecule is going to be 100% transferred into the oxygen molecule. No energy is going to be lost to the environment. Okay, so the kinetic molecular theory, lots of good assumptions for us to make as we are doing our gas law problems. Now, the way that we cover gas laws is you guys are going to work word problems. And in these word problems, It's just like any other word problem we've done this year. You're given a formula, you'll have some variables, and you are solving for one unknown variable, okay? Some things you have to know right off the bat. Every time you do a gas law calculation, the temperature must be in Kelvin. Kelvin is a system of temperature that's based on absolute zero, okay? So in order to convert from your degree Celsius temperature to Kelvin, we're going to add 273. So anytime you see a temperature, make sure that it's in unit of Kelvin. Now, the second thing that you need to know is you're going to start seeing this abbreviation STP again. You've already seen this abbreviation when we went from mole island to liter island. So this was liters of gas at STP. Okay, so you learned this back in Unit 7. So I just wanted to refresh you and remind you that STP stands for standard temperature and pressure. And standard temperature is 0 degrees Celsius. Standard pressure is 1 atmosphere. Okay, so what we're going to do today is we're going to look at the combined gas law formula. Okay, so within this formula, technically, I could teach you 4 different formulas. And as you've probably already heard, you do not get a formula sheet on your SOL. So instead of teaching you 4 formulas, I'm teaching you one that we can apply to all, okay? And that formula is PV over T equals PV over T. So within this formula, I have 3 kind of laws that we can talk about. Boyle's law, Charles's law, and Gay-Lussac's. Okay, so Boyle's law says that pressure and volume have an inverse relationship. And so you've learned from math class that that means that if you increase the pressure, your volume is decreasing and vice versa. Right? So if I wanted to draw a graph of that with pressure on my X and volume on the Y, increasing pressure would mean that I'm moving from left to right. Decreasing the volume would mean that I'm coming down the y-axis. And so here's what the slope of our line would look like. Okay, these are all relationships that you have hopefully learned and recovered in Algebra 1 and Algebra 2. Now, what we can do is, if I'm reading a problem and it only talks to me about pressure and volume, then I'm working within Boyle's law, and I can just ignore the T. So PV equals PV, there's Boyle's law. Okay, now Charles's law says that volume and temperature have a direct relationship. Okay, so that means that if I increase the volume, I increase the temperature. So if I'm drawing a graph, temperature on the X, volume on the Y, increase temp, increase volume, there's the slope of my line. So the way that we are applying it is you read a word problem and it only gives you volume and temperature as your variables, then our Charles's law formula is V over T equals V over T. Easy enough. And so hopefully you can kind of deduce the variables that Gay-Lussac's is going to use. So Gay-Lussac's says that pressure and volume have a direct relationship. Okay, so I increase P, I increase V, and vice versa. Temperature, pressure and temperature have a direct relationship. Increase P, increase T. So here's what the slope of our line would look like. Okay, so if you are working a problem that only gives you pressure and temperature variables, then you're using Gay-Lussac's law and you just cover up the volume. So moral of what we're doing, here is our go-to formula. PV over T equals PV over T. If something is held constant or a variable is not mentioned, you can ignore it. Sometimes if we use the combined gas law, which is technically the formula that I have written here, you will have 5 different variables and you're solving for 1. Okay, so I want you to go to page number 1 of your Unit 11 book. Go ahead and write your formula at the top of the page. PV over T equals PV over T. Make yourself a note to put temperature in Kelvin, and let's get going. So, number 1, the highest pressure ever produced in a lab was about 2 times 10 to the 6th atmosphere. If we have a 1.0 times 10 to the 5th liter sample of a gas at that pressure, then release the pressure until it is equal to 0.275 atmosphere, what will the new volume of that gas be? So the first value I'm given is a pressure value, so 2 times 10 to the 6th ATM. And then it gives me a corresponding volume for my gas, so 1.0 times 10 to the negative 5th liters. So this is kind of like in Unit 10 when we learned how to do the dilution problem, and you have to be able to match up conditions, like this is our gas initially, this is what it looks like finally. So then it says that we release the pressure, so there's a new pressure value, 0.275 atmospheres. And then it says, what will the new volume be? So from looking at my variables that I have, PV, PV, I'm not using temperature at all. So I can use Boyle's law, PV equals PV. And then I'm just going to plug and chug. So 2.0 times 10 to the 6th atmosphere times our volume equals 0.275 ATM times our X. So multiply and divide, do some algebra here. Be careful as you're plugging and chugging. So our X is going to be 72.7 liters. I have atmosphere here. It would divide by those atmosphere and give us liters. Okay. This is algebra 1, y'all. Algebra 1. You should be able to very quickly be able to solve for an unknown. So I am purposefully not completely explaining the algebra because this is Unit 11 of a chemistry class. You should be able to do algebra. Okay, let's examine our relationship a little bit. I went from 2 times 10 to the 6th atmospheres, so that's very large, to a very small amount of pressure. So I decreased the pressure. So using Boyle's law, I should see an increase in volume, which we see. 1 times 10 to the negative 5th to 73 liters. So that is an increase in volume. Okay, let's look at number 2. Number 2 says, on hot days, you may have noticed that potato chip bags seem to inflate even though they have not been opened. If I have a 250 milliliter bag at a temperature of 19 degrees Celsius and leave it in the car, which has a temperature of 60 degrees Celsius, what will the new volume of the gas be? So I have a volume of 250 milliliter. I have a temperature of 19 degrees Celsius. Because this is a gas law problem, I have to convert that to Kelvin. So that is 292. It says, what will the new volume be when I change the temperature to 60 degrees Celsius? So that is 333 Kelvin. So our formula, PV over T equals PV over T. My problem makes no mention of pressure at all, so we are going to ignore it. And so our formula is V over T equals V over T. So then I plug and chug. 250 milliliter over 292 Kelvin is X over 333. Do your algebra, pause the video if you need to, but that should give you X is equal to 285. And again, by Unit 11 of chemistry, you should see with your units canceling, we have 285 milliliters as our final answer. So my temperature went from 292 to 333, so I increased the temperature. I should increase the volume because it's a direct relationship. I went from 250 to 285. That fits. Okay, so number 3. A gas that has a volume of 28 liters, a temperature of 45 degrees Celsius and an unknown pressure has its volume increased to 34 liters and its temperature decreased to 35 degrees Celsius. If I measure the pressure after the change to be 2 atmosphere, what was the original pressure of the gas? So, volume equals 28 liters. I have a temperature of 45 degrees Celsius plus 273. So that's going to give me 318. I don't know the original pressure. Now I have a new volume of 34 liters. I have a new temperature of 35 degrees Celsius, which is going to give me 308 Kelvin. And then my new pressure after all of these changes occur is 2 atmosphere. So when you look at your formula, PV over T equals PV over T, I am using every single variable this time. We can't just use Boyle's, Charles, Gay-Lussac's law to predict what's going to happen. I have too many changes going on. So I can plug and chug. So I'm solving for my new pressure. Okay, so we're solving for pressure. Do some algebra here. Pause the video if you need to. And so you should get 2.51 ATM as your answer. Okay, get 2.51 ATM as your final answer. Okay, number 4. Calculate the final pressure inside a scuba tank after it cools. So I have 1000 degrees Celsius plus 273. The initial pressure is 130 atmosphere. My new temperature is 25. Which gives me 298 Kelvin. So this problem, I'm back to just using 4 variables instead of all of them. So PV over T equals PV over T. Volume's held constant, and we can plug and chug. So 130 you can make a little prediction. I decreased my temperature, so my pressure should decrease. And so with algebra, I get 30.4 ATM. Okay, so that's basically it for this lecture on gas laws. So if you need more practice, complete page 2 to 3, page 2 and 3. Excellent practice on this lecture for gas laws. And then we also have a couple of extra pages in the back. Page 9 for Boyle's law, page 10 for Charles, 11 for Gay-Lussac's, and then we even have extra problems on page 12 for combined. So I think page 2 and 3 is the best worksheet because it randomly asks you questions about properties of gases, and then the actual problems are mixed up. But pages 9, 10, 11, and 12 also help you practice gas laws using our formula PV over T equals PV over T. Thanks for watching.